Welcome! This video will give you an overview of some of the key concepts from Einstein's theory of special relativity. I'll talk about how distances, times and velocities are transformed at speeds near the speed of light. I'll also talk about some of the interesting effects of special relativity, simultaneity, length contraction, time dilation, and I'll go ahead and derive the Lorentz transformation, which is quite key to special relativity. First, a little background. All of you will be familiar with the concepts of spatial coordinates, x, y and z, to locate a point in space. Although polar coordinates are sometimes used where you have a distance from the origin and two angles. But to fully define an event, we need to know the time, i.e. when it occurs, as well as its position. The full set of four coordinates, t, x, y and z, are called the space-time coordinates. A key concept here is a frame of reference. That's a platform on which our space-time coordinates are measured. If we wanted to measure the coordinates of an event in London, we might use time coordinate of GMT, that's more correctly called UTC, and measure our space coordinates perhaps with the centre of St. Paul's Cathedral as our origin. If we were looking at an event in New York, we might use Eastern Standard Time and measure our spatial coordinates with respect to the lobby of the Empire State Building. And if we were measuring an event on a passenger jet plane in flight, we could use a time frame of the number of seconds since the takeoff and measure our spatial coordinates with respect to a particular location on the passenger jet, perhaps the front. It's key to say here there is no absolute frame of reference. We could use the centre of the sun or even the centre of the galaxy, but that is not an absolute reference frame. It's just another frame of reference. A key concept here is inertial frames. These are which Newton's law of motion hold. An object will continue at rest or in uniform motion in a straight line in an inertial frame. Although there's no perfect inertial frame, the surface of the Earth is an approximation, certainly in the horizontal direction. On Earth, an object will continue moving in a straight line unless slowed down by a force such as friction. Okay, let's consider an example of a boat moving along a river. The boat's moving at 10 meters a second, that's exactly 36 kilometers an hour. The river is flowing at 5 meters a second, half the speed of the boat, and with a small piece of debris carried along with the flow to the water. Okay, let's consider a coordinate system where t is the time measured from when the debris and boat are level, x is the distance along the river, y is the distance across the river, and z is the height above the surface of the river. In reference frame S, which is position A on the riverbank, then if we start from initial position of 0,002, after 10 seconds the debris has position 10, 50, 2, 0 and is moving at 5 meters a second in the x direction. From the reference frame of the boat, which we'll call S dash, then after 10 seconds the debris has position of 10 again, minus 50, 2 and 0 and is moving at minus 5 meters a second in the x direction, i.e. moving backwards in the x direction. This is an example of the Galilean transformation to move from one reference frame to another where the two frames are moving at constant velocity with respect to each other. It's simply t dash equals t, x dash equals x minus vt, and the y and z coordinates aren't affected. The velocity transformation is simply ux dash equals ux minus v. Consider two frames. Frame S' is moving with a constant velocity v in the x direction with respect to frame S. The coordinates of an event in S are t, x, y and z, and the coordinates of the same event in S' are t', x', y' and z'. At time 0, the origin of the two frames coincide. So what we want to do is to work out the transformation from S to S', i.e. the mapping txyz to t', xy, x', y' and z'. We've defined our axes so there is motion in the x direction only. So our equations become t' equals a0 plus a1x plus a2t, and x' equals b0 plus b1x plus b2t. Because there's no acceleration, these are linear functions of x and t, so there aren't any powers higher than 1. As I said before, we've defined the origin of our coordinate system, so S and S' coincide at time 0. So this means that the two constants a0 and b0 are 0, and our equations become t' equals a1x plus a2t, and x' equals b1x plus b2t. Okay, let's determine B2 in equation 2. First, consider an object at rest in the S' frame at position x' equals 0. This must move with a constant velocity v in the S frame. So x' equals 0 if x equals vt. So from equation 2 we have 0 equals b1 vt plus b2t. So b2t equals minus b1 vt, so dividing through by t, b2 equals minus b1 v. So we can rewrite equation 2 as x' equals b1 into x minus vt. According to the principle of relativity, there's no privileged frame of reference, so therefore the inverse transformation to go from S' to S should have the same form as equation 2, just with the velocity the other way around, v being replaced by a minus v, and this comes out as x equals b1 into x' plus vt', and we'll call this equation 2a. So the speed of light is the same in all frames of reference. So if we take a light signal shown as a yellow arrow, c, speed of light, equals x over t, but is also equal to x' over t'. So t equals x over c, and t' equals x' over c. We can substitute for t in equation 2, and this will give us x' equals b1 into 1 minus v over c x. Substitute for t' in equation 2a. This gives us x equals b1 into 1 plus v over c x'. So we can multiply these two equations together and it will give us x equals b1 squared into 1 minus v squared over c squared times x. Divide both sides by x. This gives us 1 equals b1 squared into 1 minus v squared over c squared. So this then comes out that b1 is equal to the square root of 1 minus v squared over c squared, a number we call the Lorentz factor, which is usually given the letter gamma. Okay, let's once again consider our light signal. In frame S, x equals c times t, and in frame S', x' equals c times t'. So we substitute for x in equation 2, and also use the fact that t equals x over c to give us ct dash equals Lorentz factor into ct minus vx over c. So we divide both sides by c. This gives us t dash equals gamma into t minus vx over c squared, which is the new version of equation 1. At low relative velocities, gamma is almost exactly 1. So if we have a velocity of 300 kilometers a second, that's over 1,000,000 kilometers an hour, then gamma is equal to 1.0000005. And if velocity is 300 meters a second, roughly the speed of sound, then gamma is incredibly close to 1. Also at low velocities, the term Vx over c squared is almost 0. Therefore, equations 1 and 2 simply become t dash equals t and x dash equals x minus vt, which are the Galilean transformations we met earlier. If v is equal to the speed of light, then gamma equals infinity and the formula doesn't work. And if v is greater than the speed of light, then gamma is an imaginary number, a square root of a negative number. So the conclusion we make is we can only transform between reference frames where the relative velocity is below the speed of light. An interesting fact of the time transformation is that events at different places which are simultaneous in one frame aren't simultaneous in another. So if you have an Earth-based observer who sees two events, A and B, to occur simultaneously, then if we also suppose we have a rocket moving at a constant velocity v in the x direction, then the time of event A in the rocket's frame is given as gamma into t minus vxa over c squared, and the time of event B in the rocket's frame is given as gamma into t minus vxb over c squared. So the time difference between these two events is gamma v into xb minus xa over c squared. So if we put some numbers in, if we assume that the rocket is moving at 7.5 kilometers a second, the separation between the events is 100 kilometers, then in the rocket's frame, event A occurs 8.33 nanoseconds after event B. Now let's reverse the direction of the rocket but leave everything else the same. So in this case, v equals minus 7.5 kilometers a second, and as before, the events are 100 kilometers apart on Earth. In this case then, ta dash minus tb dash equals minus 8.33 nanoseconds. So event A occurs 8.33 nanoseconds before event B in frame S dash. So in summary, which order events occur depends on the observer's reference frame. There's no absolute time, no absolute order of events. Consider a rod of length L measured in a frame S dash in which the rod's at rest. The rod is moving rapidly in the x direction with respect to another frame S. In frame S dash, the ends of the rod have position xa dash and xb dash. So the length of the rod is simply xb dash minus xa dash. What we want to do is find the length of the rod in frame S. From equation 2 we have xa dash is equal to gamma into xa minus vt, and xb dash equals to gamma into xb minus vt. So subtracting the first equation from the second, we have xb dash minus xa dash equal to gamma into xb minus xa. So ls is simply L divided by gamma. In frame S, the rod is shorter. It's 1 over gamma, its original length. If we take an example, if we imagine that v is 0.1 the speed of light and the length of the rod in the co-moving frame is 10 meters, it's been contracted by 5 meters with respect to the stationary frame. An interesting effect of special relativity is time dilation. Moving clocks run slow. An example of this are particles called muons. These are created 50 kilometers above the Earth's surface in the upper atmosphere and only last for 2.2 microseconds. They move at very high speeds, very close to the speed of light. So they should only be able to travel a distance of 660 meters before they decay, because their lifetime is so short, and none should reach the Earth's surface. But they do. So if you look at a muon in special relativity and call its lifetime the Greek letter tau, and we look at the muon's frame of reference, then it's created at position x dash at time ta dash and decays at time tb dash, which is also at position x dash because we're in the muon's frame of reference. What we want to do is to find its lifetime in the Earth's frame of reference. Let's call this tau e. So from equation 1a we have Ta equals gamma into Ta dash plus Vx dash over c squared. Tb equals gamma into Tb dash plus Vx dash over c squared. And if we subtract one equation from the other, then we get tau e, which is Tb minus Ta is equal to gamma tau. So let's take an example. If we have v, the velocity of the muon, is say 0.9995 the speed of light, then gamma is 100. In the Earth's reference frame, the lifetime of the muon is then 100 times longer than it is in a frame at which they're at rest, and this gives them time to reach the Earth's surface. Finally, I'm going to talk about how velocities add in special relativity. It's a little bit more complicated than the Galilean transformations we met earlier. On Earth, imagine an object moving at a constant speed u, then the x component of the velocity is given by xb minus xa divided by tb minus ta, because velocity equals distance divided by time. In frame S dash moving at speed v in the x direction, then we have ux dash equals xb dash minus xa dash divided by tb dash minus ta dash. Substituting for all the values t dash and x dash using equations 1 and 2 gives us. Then if we group all the x and t terms together on the top and bottom of this expression, it gives us dividing top and bottom by gamma into tb minus ta gives us, and since of course ux equals xb minus xa divided by tb minus ta, we have the final result. Also, if we look at the velocity in the y direction, which is of course perpendicular to v, then we have, and similarly for the velocity in the z direction. Finally, I'm going to be looking at an example of using the formula we've just derived. Imagine an object moving at 0.5 times the speed of light. Consider how its velocity appears from a frame moving at 0.7 the speed of light in the opposite direction. Well, Galilean relativity says it's simply the difference between the two velocities, which comes out as 1.2 times the speed of light. In special relativity, we have to divide this difference by the extra factor 1 minus uxv over c squared, and this comes out as 0.9 the speed of light. In fact, whatever the value an object is moving at, its relative velocity must always be less than the speed of light from any frame.